some numerical. Welcome to the optical communication course. So today we will learn some numerical there. A typical glass core optical fiber has a specified transmission loss factor of 0.046 dB per kilometer. That loss factor is due to relay scattering at wavelength of 1000 nanometer. The glass material possesses an approximate effective temperature value of 758 K. Isothermally compressibility parameter value of 8.4 into 10 to the power minus 11 m square by n here, and photoelastic coefficient of 0.245 determine the core refractive index determine the core refractive index from the view of theoretical consideration. Now here our aim is about to determine the core refractive index. We need to know about what will be the relay scattering equation, relay scattering gamma r 8 pi cube by 3 lambda raised to 4 n raised to 8 p square beta c k and tf. Now if you see that thermosibility iso isothermally compressibility parameter, that is 8.4, so we can write this isothermally compressibility parameter, that is p, okay, that is 8.4 something. Then we have the beta c, that will be considered for the what will be the value for the your from this compressibility parameter we can consider. Now we'll go ahead here, that It is given that effective temperature 785 K Boltzmann constant we have. Okay, so now we can consider that what will be the co-refractive index, that is about a n here. Now, if you see here in this expression, that relay scattering that is to be obtained, and for this relay scattering, that is transmission loss factor is about a 0.046 is given. 0.046 dB is given, that is about a transmission loss factor. So means transmission loss factor that will be of 0.046, that is given, and from that you can calculate that what will be the relay scattering using the transmission loss factor. So we can solve it for the transmission loss factor to obtain the relay scattering, that is gamma r is equal to minus 10 log of base 10, and that will be gamma, that is we have one more constant that can be obtained from this value of the given particular wavelength 1000. Okay. Now this factor eta is to be obtained, that will be nothing but a 10 to the, or you can say that this is about a factor that my transmission loss factor 0.046 is given. So we have the 10 to the minus 0.046 divided by a 10. So that will be the, will get the eta. That will become a 0.9895. If you put that in this value of here, in that case, then we can calculate that for L is equal to 1 kilometer, here that 1000, small r is equal to 0.0046 into 10 to the power minus 3. Substitute the values here in this expression, put that all the values, and after that solving, we'll get that n is equal to 1.5. That is about the refractive index of the core. Then we see that another expression for equation for the two-step index fiber exhibit the following parameter, that a multimode fiber with a co-refractive index of 1.500, a refractive index difference relative refractive index difference of 3%, means that is del, and an operating wavelength of 0.82 micrometer. That's first term, 0.82 micrometer. Second, an 8 micrometer core diameter single mode fiber with single mode fiber a co-refractive index with a co-refractive index difference of 0.3% and and an operating wavelength of 1 1.5 micrometer. Estimate for the A and B the critical radius of curvature, that is RC, critical radius of a curvature RC, at which critical radius of a curvature at which large bending loss at which large bending loss occur in both cases. Now in the first core that N1 is given, del is given, and a operating wavelength is given. Now if you see that RC, that is the critical radius of curvature for multimode fiber, that RC is equal to what? 3N1 square lambda divided by 4 pi N1 square minus N2 square. Now N1 is given, that N1 is equal to what? 1.50. Del is equal to 3%, means that is about 0.03, and that lambda is about 0.82 micrometer is given. Now you can solve it to obtain the N1. So we know that del is equal to what? N1 square minus N2 square by twice of N1 square. You can put the value of del, you can put the value of N1, you will get the N2. After solving, you will get the N2. That N2 will be a 2.115. Put that value of N2 here, have the lambda here, N1 here, and then if you put all the values of N1 and everything, then you will get that RC is equal to 9 micrometer. Then a second case, that is about a B, a core diameter is given, that is A is equal to 8 micrometer is given, that A is the radius actually, so that's why A is equal to 8 by 2. So from the diameter of core, you just write 8 D is equal to 8 micrometer. That is about a case P. That is a core diameter. So you can find out the core radius, that will be a 4 micrometer. Then a core refractive index N1 is about a 0.3. Sorry, the core refractive index, no, that is about statement. Core refractive index is same as above A, and the relative difference and a relative refractive index difference is about a 3%. Means N1 is the same, that is about earlier example, that is N1 is equal to 1.5, and del is again same, that is about a 0.3%. Means del will be what? 0.003. Instead of 0.03, it will be 0.003. And the operating wavelength lambda is equal to 1.5 micrometer. Then you can calculate that from this del and n1, you can find out n2, because a del is equal to n1 square minus n2 square by twice of n1 square. So you'll get the n2 by solving it. That will be 2.237. Then the fiber is given, that is about a single mode fiber with a core refractive index and all the values, and that is operating at an wavelength of 1.5 micrometer. Okay, operating wavelength. Then we need to calculate that what will be the cutoff wavelength for the single mode fiber. So lambda c for single mode fiber, that will be what? Twice pi a into n1 twice of del raised to 1 by 2 divided by 2.405. This 2.405 is a V number, and above that, then your fiber will work at a multimode 1. That is cutoff V number for a single mode fiber. It will operate 2.405, so that we can calculate that cutoff wavelength. So put all the values, we will get the lambda c is equal to 1.214 is the answer for this cutoff wavelength. A is what? 4 micrometer. Then we calculate what will be the radius of a curvature for the single mode fiber. That will be 20 lambda n1 minus n2 raised to 3 by 2 into 2.748 minus 0.996 into lambda by lambda c raised to minus 3. After solving, we will get that RC for the single mode fiber. So RCS for the single mode fiber, it will be of a 34 mm. That is about a cutoff wavelength for the given particular fiber. Next, determine the transmission bandwidth. Determine the transmission bandwidth of 300-meter optical fiber of 300 optical fiber cable having a specified bandwidth length product of 600 megahertz. So bandwidth length product means what? We have a bandwidth into a length that will be of 600 megahertz into kilometer. Okay, megahertz into kilometer. That is bandwidth length product. Now, for a 300-meter of optical fiber, so bandwidth of a optical fiber is nothing but what? What will the bandwidth length product? That will be of 600 megahertz per into kilometer divided by a 300 meter. We can calculate in terms of kilometers. So 10 to the power minus 3, that will be the kilometer. So it will give us the 2 into 10 to the power 3, that will be the megahertz. So bandwidth, that will be a 2 gigahertz. 2 into 10 to the power 3 means what? T into 2 into 10 to the power 9 hertz. So 9 hertz means what? Gigahertz. So that's why it 2 gigahertz. So that will be the bandwidth. Next one. An optical fiber cable has a specified bandwidth, length, product of 500 megahertz to kilometer. If it is required to obtain a transmission bandwidth of 85 megahertz for a particular mode of propagation, determine the maximum distance that can be used between repeaters. So bandwidth length product, so that will be what? If 500 megahertz into kilometer, this one is nothing but a bandwidth and this one is for the length. So maximum distance between the repeater is equal to 500 megahertz into kilometer divided by a bandwidth. So for the given bandwidth, so if you consider that bandwidth of what, 85 megahertz here, then maximum distance between repeater is equal to 500 megahertz into kilometer divided by 85 megahertz. So then it will be of a 5.9 kilometer. That is about a maximum distance between the repeater here. So similarly, we have the numericals for the pulse spreading, distortions and all. We'll go ahead with a one example here. A 6 kilometer optical link consists of multimode tape index fiber with a co-refractive index of 1.5 and a relative refractive index difference of 1%, estimate a the delay difference between the slowest and a fastest mode at the fiber output. Then B, the RMS pulse broadening due to intermodal dispersion on the link. Then C, the bit rate, maximum bit rate that may be obtained that may be obtained without substantial error, without substantial errors on the link. Wait. On the link, assuming only assuming only intermodal dispersion assuming only intermodal dispersion. Then D, bandwidth length product corresponding to C. Now we consider that here that's about the first the delay difference for the slowest and fastest mode. Because we say that we have a spectral width of the component. This one is about a spectral width. So in that case, we have the various frequency components. Means we can say that Fn to Fn. So now this frequency component will come faster and this will come late there. Means slowest and faster component. When we transmit the signal from the fiber, in that case, this one is about a spectral width for your source. So it has a different frequency component. So that's why the pulse broadening takes place when we transmit simple pulse from the fiber there. So that's why we need to know about the delay difference. And the delay difference is nothing but del delta Ts is equal to what? What will be the length of the fiber, then your co-refractive index and the differential. So if you put that length is about a 6 kilometer, and a refractive index for the core is about 1.5, and the difference percentage, that is about 1%. So that will be 0.01 divided by 3 into 10 power 8. Then you will get some answer. That is about a 300 nanosecond. Next, RMS pulse broadening due to intermodal dispersion, that is sigma s, that is L n1 del divided by 2 under root 3 into C. So all other constant term, only 2 under root 3 will be adding. So that answer will be 836.7 nanosecond. Then see what will be the maximum bit rate here. So maximum bit rate that may be obtained without substantial errors on the link, assuming only intermodal dispersion. So that will be is equal to twice of del ds here, because of it is nothing but a delay difference. So if we calculate that, so 600 into 10 to the power minus 9, so that will become say 1.7 megabit, okay, per second. But here we have to consider that a RMS pulse broadening. So in that case, maximum bit rate is nothing but what? A zero point 0.2 divided by your sigma m. So that is about a pulse broadening, that is sigma s same. So it is about 0.2 divided by 86.7 into 10 to the power minus 9. So it will give us 2.3 into megabits per second. So here this is about the maximum bit rate we obtain because of the delay difference. So this one is about the improved estimate based on the pulse broadening. This one we are getting because of that RMS pulse broadening. So we are getting the bandwidth for the system, that will be 2.3 megabits per second. Then these are bandwidth link product for the above. So bandwidth into length here is about a 2.3 megahertz into a 6 kilometer. Then answer will be 13.8 megahertz into a kilometer. That will be the bandwidth link product. So this one just we stop here for some numericals. Now time to continue with a MCQ here. Okay. So now for the model 2 to MCQ we'll see. Okay. So I'm just writing the question here. All of you please type your answer in a chart. Question 1, no need to write. Signal attenuation in optical fiber communication is A, the ratio of input optical power into fiber to the output optical power from the fiber. And B, the ratio of output optical power from the fiber to the input optical power into the fiber. C, depends on input power to the fiber. D, depends on output power from fiber. Now type the answer. What will be the answer for this? For the signal attenuation inside the fiber here. What will be the answer for this here? What will be the ratio? Right? Correct? That is that input optical power into the fiber to the output optical power from the fiber. That is about the A. Next, the material. Next, the material absorption loss in optical fiber depends upon the material absorption loss in optical fiber depend on A, the material composition, then B, the fabrication process of the fiber, then C, both A and B, and D, none of the above. Now type your term, right? It is a C. It is about the material composition. What is the material composition of the fiber? As well as that the fabrication process. It's supposed to be some blur or some holes or some bubbles or something else occurs. So material dispersion occurs. Dispersion is nothing but a pulse broadening. Next one, extrinsic absorption in optical fiber is due to A, material impurity, then B, found in glass. Okay. Then its basic material structure, basic material structure in the near infrared region. Then C, transfer of optical power from one mode to same mode or other mode. Then D, transfer of optical power from one mode, sorry, transfer of optical power from one mode to the mode into different mode linearly. That is C. Okay. Then transfer of optical power from one mode to same mode or other mode in either forward or backward direction at a different frequency. Now answer for this. Extrinsic absorption in optical fiber is due to material impurities found in a glass. Then B, its basic material structure in the near infrared region. Then C, transfer of optical power from one mode into the different mode linearly. Then D, transfer of optical power from one mode to same mode or other mode in either forward or backward direction at a different frequency. What is the answer for this? The answer for this is about A. Extrinsic absorption is because of the material or a metal impurities found in a glass. Okay, extrinsic absorption in optical fiber, it is because of that impurities found in a glass. Okay, inside the material, whichever the glass fiber we are using. So that's why it is available in that particular fiber. Next question, nonlinear scattering losses due to nonlinear scattering losses due to option same A, B, C, D. Now this option is for the extrinsic. Now these are the three options you have. Its basic material structure near infrared region, then transfer of optical power from one mode to the different mode linearly, or transfer of optical power from one mode to the same mode or other mode in either forward or a backward direction at a different frequency. Please type your answer fast. Transfer of optical power, right? Correct. It is a D, transfer of optical power from one mode to same mode or other mode, either forward direction or backward direction. That is about a scattering. Okay, non-linear scattering means what? Stimulated beryllium scattering and a Raman scattering. It is about a forward, okay, or a backward. SBS, that is about a backward. Raman scattering, a forward one. Okay, that is about a non-linear scattering. That is answer is about D here. Correct. The next one,